Java Virtual Machine is the backbone of the Java platform. It is responsible for its hardware and operating system independence, the small size of its compiled code, and its ability to protect users from malicious programs. As per its official definition, Java Virtual Machine is an abstract computing machine, and there's a reason for calling it a machine. While it's not a physical machine like a real computing machine, it has its own instruction set and manipulates various memory areas at runtime. Well, there's an interesting thing about the JVM. It knows nothing about the Java programming language. It knows only a particular binary format, the class file format. And a class file contains the Java virtual machine instructions, or bytecodes as we call them, and a symbol table, as well as other additional information necessary to complete its job. We often say that the Java is so secure. So it is very much because of the Java virtual machine, which imposes a strong syntactic and structural constraints on the code in a class file. But it's not that it will only host or run a Java class file. Any language with the functionality that can be expressed in terms of a valid class file can be hosted by the Java virtual machine. Now, the question is, why do we need to know about the JVM? Why, being a developer, we need to know about the internals of the JVM? Well, the one line answer is that you need not to. One can continue to work and develop apps in Java without knowing too much about the internals of the JVM. But if you are interested in the performance of your application, then sooner or later the JVM will fall in your way. And then naturally you will feel a need to understand its basics. Understanding JVM's internal architecture will help you to write better software and help in investigating the performance related issues. So, JVM is an important component of the Java technology architecture. Java technology architecture is a broad thing, and it uses the following to fulfill its goals. It uses Java Virtual Machine, the garbage collection process, Java runtime environment, and a whole set of JVM tool interface. Now the question is how the JVM works. So it is broadly speaking a two-stage process through which the JVM works: interpreting and class loading, and executing the bytecode. According to the specifications of the language, JVM is a stack based interpreted machine. So instead of having the registers like a physical hardware CPU, it uses an execution stack of partial results and perform calculations by operating on the top value or values of that stack. So when we launch our application using the Java command, the operating system starts the virtual machine process. This sets up the virtual environment and initializes the stack machine that will actually execute the user code in your .class file. The entry point into the application is the main method of your xyz.class file. In order to hand over control to this class, it must be loaded by the virtual machine before the execution can begin. And for that purpose, the class loading mechanism is used. When a new Java process initializes, a chain of class loaders is used. The very first class loader is known as the bootstrap class loader. It contains the classes related to Java runtime. Earlier, these classes were loaded from the rt.zar file. From Java 9 and onwards, this process of class loading at the bootstrap level is somewhat different. So, as clear from the name itself, the main work of the bootstrap class loader is to load the classes that are needed to bootstrap the Java application. These are the minimal set of classes like java.lang.object or the class object and class loader, etc. A class loader is an object which is responsible for loading the classes. The class loader is an abstract class. Every class object contains a reference to the class loader that defined it. These classes then allow other class loaders to bring up the rest of the system. After Bootstrap, the extension class loader is used. And if we talk about the hierarchy, the Bootstrap class loader is the parent of the extension class loader. Extensions are not widely used, but sometimes they can supply overrides and native code for the specific operating system and platforms. Like in the case of Java 8, the Nashron JavaScript runtime was loaded by the extension class loader. And finally, we have the application class loader, which is responsible for loading in user classes from the defined class path. Some people call it as the system class loader, but that's not the right way to refer it. Simply because it does not load the system classes like the Bootstrap class loader. So, if we talk about the broader hierarchy, it is the child of the extension class loader. Bootstrap class loader is at the top. Then we have the extension class loader. And then finally, we have the application class loader. Now, you can ask if all the classes have been loaded by these class loaders at different stages. Then, when we get and how we get the class not found exception. So, we need to see that if a class loader fails to find the class, a class that is specified as per the specs of the JVM, the typical behavior is to delegate the lookup to the parent. If the chain of lookup reaches to the bootstrap class loader label and the class is still not found, then a class not found exception will be thrown. Java only loads a class once, and class object is created to represent the class in the runtime environment. Sometimes the same class can potentially be loaded twice by different class loaders. So that's why a class in the system is identified by the class loader used to load it as well as the fully qualified class name, which includes the package name as well. So, in a nutshell, a class loader performs the three main tasks: loading, linking, and initialization. Loading means the class loader reads the bytecode of a class file and creates a class object that represents the loaded class. Linking is a process which includes verification, preparation, and resolution. Verification of the loaded class, verifying that the loaded class is valid and conforms to the Java language specification. Preparation means allocating the memory for the class variable and setting their default values. And resolution means the class loader resolve references to the other classes and methods by searching for the classes and methods that the class depends on. And the final step that is performed by the class loader is initialization. Class loader initializes the static variable and runs the static initialization blocks of the class. So that's all about the first stage of the JVM functionality, which is interpreting and class loading. The second stage is executing the bytecode. Java source code goes through a significant number of transformations before execution. The first transformation is the compilation step using the Java compiler javac. The job of the Java compiler is to convert Java code into the .class files that contain bytecode. Some optimizations are done during this process, and the resulting bytecode is an intermediate representation that is not tied to a specific machine architecture. And this decoupling from the machine architecture provides the portability. That is what we call compile once and run everywhere, meaning already developed or compiled software can run on any platform supported by the JVM, and this provides an abstraction from the Java language. So, with Java comes a class file deassembler as well called the JavaP that helps in inspection of the .class files. Using the JavaP command from the command prompt will provide you the complete bytecode from the class file. And using this command with -v option can provide you the full class file header information, constant pull details, and everything. So that's all about the broader understanding of the JVM's functionality. So far, we have discussed the top part of the JVM architecture, but there are other aspects as well. As we can see in this diagram, we have the whole stack of the JVM memory, then there is execution engine, native method interface, and native method libraries working together in this architecture to provide the complete functionality of the JVM. We'll try to cover all that in the next part.